seminars. So my name is Licia Capra. I am a professor of pervasive computing in the department, and I'm also acting as a head of the Autonomous Systems Research Group. And I guess we've made it our New Year resolution for 2021 to finally kickstart this seminar series we've been talking for a while. So our group is quite broad in terms of research topics, and we cover things from robotics to vision, machine learning, all the way down to computational social sciences. So what we want to do with this seminar series is invite external speakers, which are renowned experts in these fields, to talk about this broad range of topics. And I'm very happy that Dimitrios has organized this first talk. So I will pass the mic to him, who is going to introduce our speaker and the topic.
All right, thanks a lot, Licia. I see, by the way, that some people are in Microsoft Teams, so I guess that they will join as soon as possible. I see Steve here. So first of all, welcome to the new series, everybody. It's my great pleasure that the first speaker is a very good friend of mine and a great researcher in the field of robotics, Professor Kostas Alexis. So let me give you a little bit of bio of Costas before his talk. So Costas did his PhD in University of Patras in Greece and graduated in 2011. And then he moved to the famous Autonomous Systems Lab in ETH in Zurich from 12 to 2015, when he became professor in University of Nevada in Reno until recently. He got tenured there, and recently he moved to in 2020, right, really a few months back, in the Department of Engineering Cybernetics at the Norwegian University of Science and Technology as full professor. So today he's gonna, if you're following the news, Costas is also connected to the DARPA Subterranean Challenge. And if you're following him, please check all the videos that they're producing there and the research there. It's amazing. So today he's going to talk about field-hardened, resilient robotic autonomy. Kostas, thanks a lot for coming, and we look forward for the talk. Thanks a lot. Over you go.
Thank you, Dimitris. So I will start directly. I want to thank everyone for being here today and attending the talk. And I'll start from the idea and the basic direction behind what we are presenting today and what we call field-hardened resilient robotic autonomy. I think that immediately there's a very large community now in robotics that pushes the frontier for autonomous systems. And I think the particular focus of our team relates to the fact that when systems are expected to be deployed in largely unknown, visually degraded, challenging environments for which robots still play the role of the early explorer, the unit that will go map and characterize the environment possible before any human entry. And in these conditions, I will say that the major challenge is that it's just enough that one part of the autonomy is enough to break for the whole autonomous operation to be fragile and therefore not being able to continue. So what we're focusing in our research is what we call resilience in autonomy. And we define resilience through three major branches. That we say that a robot is resilient if it is robust, for example, robust against disturbances and other effects of the environment. If it presents the property of redundancy, so we aim and try to facilitate that it is not that it is enough to be able to operate when everything is always fine, all sensors are working properly and so on and so forth, but there has to be some extent of redundancy. And we also say that the system is resilient in its autonomy if it is resourceful. That means that if it has one way to solve a particular problem, for example, one way to solve the slum problem, but this particular way fails or it renders itself ill-conditioned in a certain environment, then there must be an alternative solution on board the robotic system to maintain and retain its autonomy in its operation. So in particular, we focus on this challenge of accessing, navigating, mapping, and searching very challenging high-risk environments, and good examples of that relate to the DARPA subterranean challenge that Dimitris mentioned. For example, as it relates to underground mines and so on and so forth, what you essentially see on the image on the right. So in these conditions, we aim to facilitate how the robots can enter, get no prior knowledge for the environment, and explore on their own. And you should be able to see instances of that on the video there on the right, with the robot exploring an underground mine in northern Nevada. And there's a collection of applications that relate to this research domain, and we have been honored to be funded by a set of agencies from the US, DARPA, NSF, Department of Energy, NASA, and others, and also here in Norway from the Research Council the last 2 months. And in particular, with respect to the challenges that we face in this type of deployments for which we try to facilitate what we call a resilient autonomy, we consider 3 major challenges. First of all, that is not only GPS denied, so you don't only need, for example, to have one way to estimate the odometry and the map of the system subject to lack of GPS, but also that we have conditions of perceptual degradation. And in particular, we organize them in 3 major fashions: that it is dark, which is kind of reasonably easy to overcome; that it is obscurance filled, so this is essentially dust, fog, moist, smoke, and so on and so forth; and that it can be geometrically self-similar, especially, for example, underground environments that are man-made, in particular, such as tunnels, can be self-similar in their geometry. And then at the same time, the geometries we have interest should, or we consider that they may present the property of being simultaneously very large scale and very narrow. So there are areas that can be 20 meters wide, 30 meters wide, 40 meters wide. A cave, for example, the final stage of the DARPA competition will take place in a cave. Rooms of caves can be 30 meters wide, 40 meters wide. Actually, if you search a little bit online, you will see that there exist caves that are massively wide on Earth. And simultaneously, the same cave networks in certain sections become as narrow as 1 meter or less, right? Whereas even a human person struggles to navigate through. And we also assume that there is no teleoperation infrastructure deployed a priori. This means that if we want to have communications between our robots, then the robots must self-deploy this communication infrastructure as they operate. So we have these kind of conditions. All together, we relate them to what we call austere navigation and austere autonomy, that everything that has to be both, there's no abundance of resources on the system. Everything must be based on what the robot can implement and facilitate in the challenging environment. All right, so then we have the kind of basic 4 research fields that are nothing new to anyone working in robotics, but in particular for us, perception. We particularly focus in the domain of multimodal perception. I will explain in a second. On the control side of robots, and of course on the pathfinding capabilities, especially the pathfinding capabilities that interplay with the limitations of the onboard perception. And at the same time, as we focus on fundamental research, we also seek to develop the prototype systems that can realize and demonstrate these capabilities in the field, in the actual environment. So that's also the idea behind what we call field-hardened robotic autonomy. So I will focus initially on the first major research question that we try to work with, that of sensing degraded multimodal perception. So consider please an environment that presents all the 6 challenges that we saw there on the right, that it is GPS denied, there is no illumination other than what the robot is bringing on its own, that we can have certain types of obscurance, for example, dusk, for example, fog, and so on and so forth, that it can be self-similar, multi-kilometers in possible scale, and also at certain sections can be extremely narrow. Now, let's also assume for the rest of this discussion that these challenges do not appear all of them simultaneously. So we don't have a condition that it is simultaneously GPS denied, dark, obscurance field, self-similar, and it's a super 1 kilometer long, 1 meter wide tunnel. But let's say that other than GPS denied, the other challenges appear maybe 2 or 3 of them together, but not all of them together. So the basic idea is that under such an assumption, the key observation is that we can have different modalities that each of them individually sustains, one of the modalities will sustain any condition as they present themselves, but some modalities will fail at every given situation. So when we have a ladder system and we are in a self-similar tunnel, it is very possible, if it's truly self-similar, that localization mapping based on LiDAR will be ill-conditioned, and at this point we cannot register the maps, and therefore we cannot estimate also the odometry of the robot. But in these conditions, it wouldn't be impossible, and we will show data for that, that we might have visually informative conditions, or that it is thermally informative, that there is sufficient gradients in the thermal image. And vice versa, we can have a situation that it is non-self-similar, but otherwise can be extremely dark and so on and so forth. So from all those, because in the interest of time, I only pick those that I think are most interesting, we're going to show two basic directions. One of them will be thermal inertial odometry, so the capability of using radiometric data to estimate the odometry of the robot, and then a complementary multimodal fusion architecture to combine the modalities and have a resilient slump solution that works in all these conditions of degradation that I mentioned. So let me start from the overall architecture before I go to the specific of thermal inertial odometry. The current methodology as it is deployed in our robots in the DARPA Subterranean Challenge, for example, is what is more or less visualized in this diagram. And this relates both to our flying robots and to the robots from our colleagues that deploy the animal system as part of our team. So we have LiDAR, odometry and mapping capabilities. When we do LiDAR odometry and mapping, we get a prior from visual inertial or thermal inertial odometry, or both. We evaluate the quality of these odometries from visual inertial and thermal inertial schemes by factorizing the variance, and particularly through the de-optimality metric. And we will explain this in a second. And then this supports the LiDAR odometry and mapping. If we detect that the registration of point clouds is ill-conditioned, we pass through the visual inertial or thermal inertial or the combination of the two odometries without essentially allowing the ill-conditioned result of LiDAR to dominate our solution. And eventually we have a system that should perform in all conditions. I will explain this a bit more in a bit more detail in a second. But in particular now, let's take one component, let's take the thermal inertial component and focus on it a bit in detail. This is a video we collected in preparation for the first year of the DARPA Subterranean Challenge. As you can see there, the robot, it is in a dusty mine. And of course, due to also its propellers, this is also a flying system, there is a significant amount of dust around the robotic system. So what we developed is that we observed through our data that although visual inertial odometry can be ill-conditioned at this point, and also very similarly in dense dust, even LiDAR is not informative anymore because simply you get wrong estimates of the point cloud or no estimate of the point cloud when the dust is very close to the sensor. Thermal inertial odometry survives, and you can see this on the images on the top. Now, not only these images are unaffected by the dust due to the size of the particulate of dust that is essentially applicable to these types of mines. Anyway, all typical dust that we know in our normal life. At the same time, we have to deal with a challenge that there are in thermal frames. First of all, gradients are not necessarily equally strong. And B, most, of course, algorithms, as we take them directly from libraries in computer vision, are made for 8-bit images as opposed to the 16-bit in general radiometric images that we acquire from thermal cameras. Now, this wouldn't matter if it wasn't that the gradients are not actually extremely strong. And because they are not strong, the gradients have to be calculated over the full 16-bit radiometric information of thermal camera images as they truly come from the driver of the sensor. So what we have developed essentially, which is the work of my first PhD at my group, Sheriar, who is now a postdoc at ETH in Zurich, is what we call KTIO, stands for keyframe-based thermal inertial odometry, and operates on the bifurcation between the front end and the back end. On the front end, we are using essentially gradients to directly associate frames, the current frame, with essentially a sliding window of keyframes selected as the robot navigates in the environment. We refine the search so as to make better association of the key points selected, again, due to the fact that gradients are not extremely strong in thermal frames, and we have to spend some extra computational effort to make the association more robust. We develop the associations from consecutive keyframes to the last current and temporal frame, and we are able to acquire the constraints for the optimization problem. We utilize IMU, which is time synchronized and calibrated, of course, with a thermal camera in the backend optimization, and this allows us to estimate robustly the odometry of the robot and to a certain extent reconstruct a key point map of the environment. Now, in particular, the main error that relates to the thermal part relates essentially to the reprojection error based on the radiometric information of the thermal frame. Again, this is important to highlight. For efficiency, we utilize a pyramid for which we start the alignment at the higher level, and then we go coarse to fine improvements on the lower levels of the image. We scale, we weight the error based on the covariance that comes from the landmark. So essentially the inverse of the covariance, which corresponds to the information matrix. And similarly, we have also the IMU error terms also scaled by the corresponding information matrices. And this allows us, again, the key idea behind this is that we needed to develop a method that operates on thermal frames. It is tailored to the specificity of thermal data, providing 16-bit thermal calibrated radiometric information. And we also particularly focus on keyframe-based approaches because the associations are not so robust as compared to traditional visual frames in normal conditions, such as operating in an office, that we had to benefit from the advanced robustness that the keyframe-based optimization over a reasonably sized window has to offer. And you see this in this result, for example, here. This is going to be one of our videos. Again, this is in the preparation of the SAPTI challenge. I'm going to show some results of the challenge a bit later. This is a mine in Nevada. We start from this entrance to the gate. You see the April tags. This is because DARPA wants us to always align against a fixed gate. So this is us replicating that we have to align ourselves against this gate. And the robot will enter the underground mine. The operation is also autonomous, but that's not really the point of this video. We have also added a fog machine to create more fog in the beginning. The key message here is that thermal inertial odometry is unaffected by these conditions. And although LiDAR also persists and operates well in this environment, so in this situation, when you combine thermal inertial odometry and LiDAR, you have an improved result, but otherwise LiDAR should also sustain the operation. We have a collection of videos and results that we demonstrate that essentially the system cannot operate, LiDAR cannot operate when the smoke or the dust or the fog is very dense. Sometimes I have already also watching the presentation as it's being displayed to you. Sometimes I see due to the connection, the videos are pixelizing. So excuse me for that, but otherwise the videos are all available if you want to have a look afterwards. What is important here now that the robot is moving more slowly, so it's easier for you to see also with no pixelization, is that in these environments, it's not always obvious that you have significant thermal gradient. And actually in caves that are truly underground and they correspond to stable environments that are natural and people are not entering inside, thermal gradient is not strong. Thus, the importance of utilizing the full 16-bit radiometric information. Otherwise, here we are demonstrating that the system is as robust as traditional thermal inertia, as traditional LiDAR odometry mapping. Now, we have also tested this against other frameworks, and this is not to mention that our work is better than other methods compared here. What we are demonstrating is that traditional visual inertial or visual odometry frameworks are not designed to be utilized right off the shelf with thermal inertial data. So this is to demonstrate that essentially you need some additional work on, even if you want to take a visual inertial framework, and if you don't want to use our approach, for example, KTIO, there are messages from this work that can be translated to other VIO frameworks with respect to how to modify them to make them more applicable to thermal inertial data. So the reason, for example, why OCFIS here is not performing very well, it's not because the method is otherwise weak. On the contrary, it's particularly strong. The main reason here relates to the path association that is happening between the thermal frames due to the character of the thermal images as compared to visual images for which OCFIS was developed using the BRISC feature. All right, there are also additional set of results in relation to that. We also have fusion between thermal and visual data together, and we weight essentially different parts of the image based on the spatial entropy of each grid cell that you see there on the right, with the purpose of being able to compare which information, the visual or the thermal, at any given point has more information to offer, which then thus allows us to retain a limited computational cost while fusing both modalities as good as possible at any given time. And you see the robot starts there in this fully foggy environment. Inside this environment, LiDAR will also not work. We have some results also that analyze this if you are interested. And when it gets also into the darker part of the workshop that this experiment is taking place, essentially visual information is completely useless, and the system ends up relying fully on thermal data at this point. All right, So if we have the individual components, and again, I'm only outlining some of the components. For example, not going through the process of outlining LiDAR odometry and mapping. We are essentially building on top of research of the community for subset of these matters. But if we have the basic components, then we can build together this architecture that we call CompSLAM, standing for complementary multimodal SLAM. And the basic idea is that if LiDAR gets ill-conditioned in self-similar geometries, but otherwise works perfectly in any environment that is with significantly rich geometry and it's not fully full of fog, for example. If visual data work in all conditions that are visually, let's say, normal. Thermal information works when there is thermal gradient in the environment and penetrates types of dust, fog, and so on and so forth. We put them together in this loosely coupled fashion that you see here, where essentially the camera inertial approach is visual or thermal, provide priors to LiDAR. Before we provide the prior, we test its covariance and we question, is it sufficiently small to be trusted? And we factorize this trust through the DOP multimetric that you see on the slide on the left. If this is the case, we actually effectively feed it as a prior. At the same time, when we're essentially aligning the point clouds to the scan alignment, we are testing if the underlying optimization problem is ill-conditioned or not through the eigenvalues that come up in the Hessian matrix. And then if this is also satisfactory, we update the solution fully, which comes from all the multimodal, all the modalities contributed into the solution. But when, for example, LiDAR ill-conditioning is detected, then we feed through purely the visual thermal inertial odometry and vice versa, right? When the visual thermal inertial odometry is above a certain value with respect to its covariance size, then we rely more and more on LiDAR odometry and mapping. And again, the idea is that these sensors are complementary. Of course, if everything happens simultaneously, it's both so similar, full of dust, dark, and so on and so forth. The solution also eventually will break. But as long as these challenges do not happen simultaneously, then the solution overall persists and survives and gives an accurate result. This is a particularly interesting, simple example. We are here in a tunnel underpass. We found this tunnel in Nevada. This is a perfectly straight tunnel that we had to essentially test our method. And what you see is that essentially the solution on the right keeps estimating the map correctly. So you see here on the right that essentially the tunnel is estimated with respect to its length. The true length of the tunnel is 80-something meters, 81, 82 meters. The proposed methodology estimates 80 meters. The original methodology that fully relies purely on LiDAR odometry and mapping approaches estimates approximately 30 meters. And the reason for that is because on the left, the original method, when it's self-similar, ends up registering the point cloud back to the original phase where it started. And therefore, essentially, the odometry is not progressing. So this is a particular case that we can demonstrate purely the effect of field condition on LiDAR information and the importance of using visual inertial data in such a condition. All right. Now, from our side, if we assume that we are in a situation that the robot can estimate its map, at least individually, before we go to the multi-robot mapping aspect, if we assume that the robot can estimate the map of its environment and estimate its trajectory in it, then the second major challenge we have to deal with, and especially as it relates, for example, to the DARPA submarine challenge, is that of being able to self-command the system so as to go and explore an unknown environment that can be a mine, a cave, an urban subterranean infrastructure, or an actual industry facility, and so on and so forth. In these conditions, we are interested for two types of problems. We are interested to explore the environment in the sense of being able to map it. So if we have a sensor that provides us depth, such as a LiDAR, we want to be able to reconstruct the point cloud of the full environment. And at the same time, we want to search the environment with respect to identifying objects of interest, which, for example, in the DARPA SAFTI competition are called artifacts. Now, because these are two different objectives, volumetric exploration and searching visually the environment or searching through any other sensor, such as, I don't know, a gas detector or something like this, we have a multi-objective optimization problem. Now, at the same time, we want, of course, to be able to avoid any collision in the environment. And as mentioned, we want to be able to negotiate environments that are kilometers long and in certain areas very narrow. We have developed a set of pathfinding methods that we are using essentially as a set of those in our deployments. So I guess it's important to just highlight all of them in the beginning, and then I will explain one of them that we tend to use more and more in our experiments. On the left, you see a method that as it explores, as it identifies the next best view for the system in a receding horizon fashion, given that it has initial no knowledge of the environment, but at any time instance has so far the area that has explored and has classified as voxels that are free, voxels that are occupied, and voxels that are unknown. We also associate a probability for every voxel with respect to how well we know if it is known or unknown or occupied. And respectively, in a second step, in a sub-optimization, we try to move the robot in a manner that repositions itself and its viewpoints so as to go to the desired destination with a minimum covariance growth. So if we are in a situation that we are, for example, doing no loop closures or whatsoever, then we want to move in this manner that either through IMU excitation or by re-observing certain landmarks, the covariance is kept sufficiently low. A second type of planner we have developed, and everything that we are presenting here is open source and available in our Git repositories. The second planner we have developed is that in the same type of architecture, in the second step, the system is focusing on areas that are visually salient. And for that, we are using progress that is available from the computer vision community that aims to replicate the human attention system. So we have an image such as the one that you see there. The fire extinguisher was the one part of the image that attracted the attention of the visual salience detection system. Then we have the graph-based exploration for subterranean environments, for which I'm gonna talk more in a second, so I'm not really presenting. And similarly, we have a set of newer methods. One method that is particularly focusing on fast exploration in this type of narrow and large-scale environments, essentially because if you are using a flying robot, your only way to do large-scale exploration, given the limitations of endurance, at some point is to increase the speed. So we want a method that focuses on fast and rapid exploration. We have a strategy that acts as an imitation learning approach to our exploration planners and replicates their performance, but at a fraction of the computational cost. There are some weaknesses, of course, because we are not retaining a map here. We are only using the last 3 point clouds for that. So will not present this in this presentation, but the paper is available for you if you have an interest. And we have a very recent method, which we call Hub Planner, which co-optimizes between visual exploration and coverage and exploration based on a depth sensor. So if you have the paradigm of a system that has a long range depth sensor, such as a 3D LiDAR, and a set of cameras, and you want both to explore volumetrically, but also to see all the environment with your cameras, which is again 2 different objectives. We have a method now that co-optimizes for these 2 objectives simultaneously and delivers a result which is improved compared to our traditional approach. Going now to our what we call traditional approach, we released this method as open source package this summer. This is the method that we are using in the DARPA Subtlety Challenge so far. And it's motivated by 2 distinct observations applicable to subterranean environments or other large-scale industry settings. A, that the environment is so large that if we are using global search in a map, it ends up being extremely complex to plan in maps that can be multiple kilometers in size. Number 1, and number 2, there exist multiple branches in these environments that the robot needs to be able effectively to do global scale planning, but we need to do this in an efficient manner. To do so, if we consider, for example, this visual diagram of an underground mine, this is a diagram of a mine in Colorado. And let's say the robot is in one particular point there and has started from the gate, from the entrance to the mine. It sits at a certain point. Locally, we can draw a bounding box only through which we can be, for example, 50 meters by 50 meters or 100 meters by 100 meters and plus minus 10 meters in height. And inside this local bounding box, we are able to, in a reasonable computationally efficient manner and with good resolution of the environment, for example, your voxels can be 10 centimeters inside every voxel or 20 centimeters, depending on the robot. We can sample a graph or motion primitives, depending on the method, and identify inside this graph, for example, a set of paths that maximize the anticipated exploration gain as it relates to if part of the environment is known and another part of the environment is unknown, of possible admissible collision-free paths that navigate the known environment, so they do not collide, but look with the sensor towards the unknown environment. We identify this path that maximizes the anticipate of how much new unknown volume our sensor will reveal in the subsequent steps of this path. And we will take the best path, or actually, in fact, a path that is both the best and refined to maximize safety in terms of clearance against obstacles. We also account for traversability for legged robots and so on and so forth, in order to be able to provide a solution that works in a variety of systems. And again, as mentioned, all these things are open source. Now, we do this local exploration, but as you obviously understand, is that if we do this local exploration in this environment, most likely we're going to guide ourselves into a dead end. We're going to explore this long branch. The robot will be happy for an amount of time that it's exploring efficiently. But when it reaches the dead end, the local bounding box might be smaller compared to where is the previous point that there is another multi-branch, another branching point for the robot to go back and continue the exploration. This is why, as we do this local search, we also simultaneously maintain a sparse graph, which now we have upgraded to what we call topological graph. And this graph, anyway, which is now computationally efficient because it only memorized a small amount of vertices, allows us to store areas that correspond to intersections or frontiers of the exploration space. At this point, we detect that we have inability to explore more locally, and we resort back to this backup, essentially, graph, which allows us to find where to go backwards in order, or not by backtracking, by going in one of the areas that we visited before, and continue the exploration from there. Once we arrive to this point, we re-trigger the local planner, and this operation continues up to the point that the robot believes that it is now the point that the remaining battery is only enough to do one more exploration step and come back. And at this point, the robot again uses the sparse graph at the global level and makes sure that it comes back to the home destination. So we can show this with an example. This is a video, and this is a robot that takes off inside this underground mine. This is the same mine that you showed before. It's a very dusty mine. It's kind of interesting from all aspects. And you see here on the bottom left and the middle plot, the path that's calculating to go and continue its exploration. So the pink path is the path that it has to follow to perceive and continue the exploration. It's using thermal inertial and LiDAR odometry mapping for its localization. And you see the calculation of these graphs, and the system continues. Now, as it's executing this exploration path, at some point, it's going to reach a dead end inside this mine. So let me proceed here a bit. So here, it's going towards the direction. Actually, there is a workshop inside this underground mine, which means that there is simply nothing else to do there. Everything is closed. So it has, however, recorded and stored this global graph. And through the global graph, it is able to continue the exploration. So this is the point. Give me a second. This is the point that it will make some additional local exploration, but otherwise returns back and goes towards a previously explored area. So it's going to go essentially to this intersection that it had met before. And from there, it will continue the exploration. This process continues, again, all the way to the point that the system identifies that the remaining endurance is only enough for the system to come back to the original home location. And this is what the robot will do eventually, right? It will just come back so as to make sure that it returns on spot. This is very important when you do these autonomous deployments, and you're not supposed even to follow your robot. Here we are following for the purpose of video, but in the DARPA competition, we have to stay outside and the robot has to perform inside. And this effectively means that we have to really have this feature that the robot comes back to the destination, or at least to a point that there is another robot with which it can communicate, and therefore all data can be effectively used. All right, and this is now the robot coming back to the destination. And the green path that you saw comes from this global graph that I mentioned before. All right, so the method, as mentioned, is not designed only for flying robots, and this is why you see us focusing on this graph-based exploration. For flying robots, we're using more of these motion primitives with respect to better performance. And here's the animal robot. This is not our work. The animal robot is just part of the RSL members from ETH that participate in our team, but they have integrated our planner. And you see here the system also accounting for traversability and being able to explore the environment. So this is common work with our colleagues. The robot here has detected an untraversable obstacle that it didn't know when it started the first path planned by the planner. So it backtracked a bit. It marked the zone as untraversable and now continues exploration. This backtracking state machine operation is because traversability calculation is more short range compared to the LiDAR point cloud view. And therefore, we have to be able to detect an untraversable obstacle as we execute a path, backtrack a bit, and then continue the operation with another path. And you see the exploration. This is a test that we conducted with our colleagues at the mine in Gonsen in Switzerland. And again, you see the same type of behavior, right? The robot is exploring, and effectively, it's going to come back to the original destination. And this is actually something that I should play. These are, again, repositioning to the frontiers detected before, and so on and so forth. And fast forward, the robot effectively will come back to the original destination. All right. So now, with respect to some particular modifications of this overall architecture, purely tailored to flying systems and fast systems, this is a collision tolerant robot. It is a collaboration. The system is developed by a company, and they're part of this collaboration of the Cerberus team that will participate in the DARPA Subterranean Challenge. And here, the robot will plan paths that are fast and simultaneously are safe. And by safe, we mean that with the end velocity of a certain path, there has been calculated in addition a maneuver that can stop the robot if needed, if, for example, there has been an obstacle that we haven't detected properly when we initially planned this path. This method allows us to go with higher speed. This particular robot we fly it with up to 2 meters per second because this is what we have identified as the maximum velocity with which it can still collide if needed, and the localization and mapping process will persist. And you see this more in a more narrow environment here. This is an abandoned mine, also in Nevada. And at some point, this mine becomes 0.8 meters in width. The robot is roughly 0.5, 0.6 meters in between these two values in width. And therefore, although we try to calculate a collision-free path, small disturbances can still lead the robot to make a small collision. And this is, on one hand, the importance of utilizing collision-tolerant platforms in this type of environments, and on the other hand, why it is important to have resilient localization when one executes this type of missions, right? So again, the whole idea is be resourceful, be redundant, be robust. And in terms of caves, I'm going to stop with general experiments now with this one. In terms of caves, there's one key message. Thermal information often is extremely weak. This is the part that the only thing that you see is some of our people inside this environment and some of the machines we brought. Otherwise, the environment is extremely self-similar. However, other modalities work beautifully in these environments. And here you see the autonomous exploration. Autonomous exploration in caves can relate a lot to the vertical component. That's why here you see the robot to always increase in height as it's executing this exploration step. Also, this means probably that a better configuration of the sensors might be of relevance to this type of environment. But otherwise, the operation that you see here is identical in principle to what you saw before. This is us performing more of field testing. All right, I mentioned in a set of the slides that a lot of this work has been done in the framework of the DARPA Subterranean Challenge. In the SubT, we are a team called Cerberus. Cerberus, for those that you don't know, is the mythological creature in ancient Greece that is three-headed dog and supposed to protect the underworld. So we got motivation with respect to the name. We're bringing legged robots and flying robots together. So that's the idea of a multi-headed robotic now system of systems underground. And it is the collaboration of my group, the Autonomous Robots Lab, RSL and ASL at ETH, Hyperlab at UC Berkeley, Sierra Nevada Corporation, Flyability, and also our colleagues from Oxford. And the overall vision is this idea that legged and flying robots possess the locomotion capabilities and navigation principles that can overcome any type of subterranean environments. And of course, this is still challenging in real life, but in principle, dexterous locomotion together with flying systems, if the localization problems are also well as addressed and the autonomy through exploration, path planning, and visual search is similarly handled well in the systems, then this robotic system of systems approach allows us to deploy from outside the subterranean area these sets of robots, either together or individually, and explore sections, share the maps, and also self-deploy communications. So these robots, the legged robot, for example, carries together deployable Wi-Fi units that it drops as it navigates. We have an additional rover, which was not in the original principle, but the rover carries a high gain antenna, and therefore, through an optical fiber connection to the ground station, allows us to establish a command post several hundreds of meters inside the subterranean environment. We cannot explore deeply with a cable, but we can establish a good high gain antenna command post further inside the subterranean setting and save us some of the first few hundred meters of needing to establish good communication to the ground station. And effectively, we can use these robots to perform the exploration fully autonomously. Maybe one slide back. These are the robots we are using. On the upper left part, you see Animal B and Animal C. Animal C is on the left, and this is the new robot we will bring to the final competition. On the right, you see two of the flying robots we utilize so far, a more traditional system that ferries all our multimodal perception pipeline, and the more collision tolerant system that you see there. And you also see the smaller rover, no, not so small actually, that we have brought to the competition carries a spooling optical fiber cable and a high gain antenna. And also at some point, we also put it perception systems to be able to support in mapping and detecting objects of interest. Now I'm going to show one result in full length. That is the instances of our deployment in the urban circuit. The urban circuit took place in February in an abandoned, actually never commissioned nuclear facility in the United States, in Satcham, in Washington. And you see their animal calculating paths based on this planner that I presented before. You see the ground rover being teleoperated with the optical fiber cable from the operator and supporting communications underground. The animal robot will do most of the exploration in these types of missions, obviously because it has the endurance capabilities that flying robots do not have. And although it operates a bit slower, it's still, right, at the end of the day, it's able to cover more range in the subterranean setting. At the same time, however, we will deploy effectively flying robots to go into areas that are hard to reach otherwise, or to cover other parts of the environment, simply because the scale of these environments is so big that one robot or two robots, here we deployed two-legged robots, are not enough to cover this environment. And believe me, we didn't cover all the environment that DARPA had in mind. I have to admit, there's still a lot of work to be done, especially as one brings systems that are research prototypes and under development in many aspects, algorithms, perception systems, and so on and so forth. But what you see here so far is the animal part. And if I speed up a little bit, you will see the deployment of one of the aerial scouts, where the system is navigating the same manner through the same planner, avoids parts of the obstacles, of course, explores parts of the environment. On the left is actually the reactor, where the area of the reactor will be. Again, there's no reactor in this facility now. It went above one of our other flying robots, keeps exploring all the way to the point that battery commands that the system has to return to the original destination. And these environments can be simultaneously complex. Sometimes they're very narrow, sometimes are visually degraded. This one was not particularly degraded. So also visual systems supported the LiDAR odometry mapping, and otherwise it was a reasonable environment in terms of localization. There are, however, some other challenges that are harder. For example, here the flying robot will try to go vertically down the stairs, and it was a successful mission, but it was successful because we had collision tolerance. So I want to mention here, you will see the robot will go down. It calculated originally a collision-free path, but as it goes to the tube of the staircase, there are disturbances. It also went slower than it had to go, so we had to have some different settings. Eventually collided with a rail, but otherwise survived the mission and went to the lower floor of this stage. And these are results that you see some of our localization and mapping results as compared to ground truth. Ground truth released afterwards from DARPA. So we show three results from Animal Badger, one of our animal robots, Animal Bear. Both these robots, again, as mentioned, developed by the group of Marco Hutter at RSL, and one aerial scout. And you see also on the table the comparison of relative and absolute pose errors. So we are utilizing the onboard SLAM capabilities of every robot. We call that ComSLAM. And we are also utilizing a multi-robot mapping framework, which not only merges the maps online in real time as the robots operate underground, assuming there is communications, of course, but at the same time improves the quality of the map as compared to the onboard odometry and mapping alone. So you see that essentially, for example, for the Animal Badger robot on the left, the relative pose error through the onboard ComSLAM was 0.19 meters. The position error, let's focus now. And the absolute position error was 1.07 meters, which is still acceptable and within the 5-meter error bound of DARPA. But the multi-robot mapping improved this result by a certain extent. And these maps here demonstrate multi-robot results. And so essentially the combined mapping from these robots as they operated what it was called the alpha course and what was called the beta course, two distinct stages of the DARPA Subterranean Challenge urban circuit. And again, I want to highlight that we didn't explore all of it. There were many, many rooms that we didn't go, many floors we didn't go. But this is research ongoing. And I want to give the credit to the people that worked on the multi-robot mapping part. You see the citation on the bottom. All right, now, as we build these capabilities that you saw before, we simultaneously identify new problems for which we were not prepared, or we did not have the solution in the beginning. First of all, we have identified the need to go through extremely narrow challenges. I also start now a project that relates to mapping and characterization of ballast water tanks, and these robots have to be able to go through as narrow settings as a manhole. So essentially, you have to fit through a 0.5, 0.4 meter size for a while. But these are actually also sizes that you once sees in natural caves. So we sat down and developed a new type of robotic platform, a new flying robot that is robust in these conditions, can navigate these very narrow environments and maintain a particularly long flight. So this is a less than half a kilo system. Currently, it's 495 grams. We are focusing on a sub 250 grams system, and it comprises of a collision-tolerant shell. It has some compliant flaps around to be able to provide compliance when it collides with an environment. It does not integrate a 3D LiDAR, of course, due to the intended weight, but it's able to go through extremely narrow settings, and its controller allows to account both for free flight and operation in contact. So this is based on old work of my research relating to hybrid mode predictive control for free flight or in contact operation with the surfaces of the environment. And you will see this result in this video. Here, RMF, that's how we call the robot, will enter initially a very narrow manhole. And inside this manhole, give me a second, it will detect the opening of the manhole. This is 0.5 by 0.4 meters manhole, if I remember correctly. The size of RMF is 0.33 meters, the rigid part. And then we have these little flaps. The flaps have 4 sensors, and we detect that we actually effectively enter the manhole. And then inside that, we are doing essentially stereo visual inertial odometry as the system navigates, and we exit the manhole. Again, there was some drift in this mission, I have to admit. So not too much, but not comparable with the results that you saw in this kind of bigger, more open environments. We also can avoid obstacles based on a more reactive scheme. This publication is currently under consideration, but if somebody has interest, you can contact me. Too fast video, so probably with Zoom. We will sustain a collision if needed, as shown in this video, and we will avoid. So it can try to avoid as many of the collisions as possible, but also if a collision is unavoidable, the system will sustain. Actually, we have this part of the video here that we demonstrate. We intentionally command the robot to go a bit to collide with the environment, and I hope the video shows that. It doesn't want to. Oh, yeah, here. So some collisions are perfectly acceptable. So here the robot collides, but through the compliance, also we have good results with respect to localization. And actually, we tested this in our motion capture. We test the system performing collisions with the compliant flaps, and we have a comparison in the paper what happens without the compliant flaps. And essentially, they help a lot in sustaining the odometry because IMU data become more informative, and also the collision takes place in longer time as opposed to the super short of having a rigid frame. All right. Now, as part of our research, I started with flying robots, and my PhD was about flying robot control, so we have not abandoned this domain at all. However, the complexity of the systems has increased. One of my talented students is currently building what we call the aerial robotic chain. We have two papers on that and one more under review. The idea here is to connect multiple of these robots in a rigid link function, and also be able to share computational resource between the robots, or sensing resource between the robots, or simply payload between the robots. So without going into details, I'm going to show one result that particularly relates to aerial manipulation, where the robot has to interact with a part of the environment. And in this demonstration, I know nobody wants this in a real robot, but anyway, the flying robot will go and open this valve, right? Or close this valve, however you want to call it. So give me a second to let the video better play. So it will position itself. This is mockup supported, so less autonomy. And it will go down. It will use this finger. And then because it has two robots, it will rotate them instead of using essentially the classical underactuated principle to create a moment. Here, we have the capability to rotate the two robots and create a significant moment, and therefore being able to rotate the valve and eventually release it and go up and come back to the original destination, right? So, and we have evaluated similarly for these purposes, robustness against typical slang load disturbances. When it already has picked something, it ends up being a system with slang loads. So there's some good robustness in this. So there should be a more intense test that nickel disturbs this robot. And also, as a final demonstration, we put this robot to play the role of flying Wall-E, or I'm sure you are all familiar with the Wall-E system. Not this part. This is just the part that we show robustness. But as you know, Wall-E, this is also a robot that tried to collect some trash and eventually go and throw the trash into a basket. Again, this is now we are outside of the field experiment domain. Nothing is necessarily very mission specific. So this is more us evaluating the robot and kind of making artificial scenarios for the purpose of evaluating individual components of the control law here. Here the system utilized the hybrid control law. I won't highlight this, and there is stability proof at every individual control mode, and reachability analysis to demonstrate safety between the switchings from free flight to hybrid and to area manipulation, from area manipulation back to free flight. Now, this was an overall coverage of a set of the activities that we do in relation to the basic loops that facilitate resilience. So in terms of perception, control, path planning, and so on and so forth, and also the system design. We have taken some of these solutions and we have applied them to a set of applications, in particular here, as it related to Department of Energy needs. Maybe some of you are familiar, back in the Cold War era, there was a lot of nuclear production, and there is something called the Manhattan Project in the US, which related to all the developments related to the nuclear infrastructure of the country. Now, there's a lot of nuclear waste out of this process, and this is stored typically in underground tunnels. So we had a project and we developed a robot back then, and we continue a new approach today that integrates scintillators. These are essentially sensors that you detect radiation and also the intensity of radiation. You can also do spectroscopy, find what type of material is inside the environment. And one of my students had developed a methodology in which we do not only 3D map the environment, but we also represent the environment based on intensity of radiation and also based on the gradient of radiation, which then in turn allows us to know what is the direction that the robot should go in order to be able to map the rest of the environment. We associate also on this MRF, essentially, the Markov random field, we also associate uncertainty with respect to how well we know the intensity or how well we know the gradient of the radiation field. And here you will see our robot, this is the ground system now, entering. We have put some buckets that contain uranium ore, so this is actual radioactive material, and we have the detection through the scintillators. Initially, the robot knows nothing, but as it goes closer, initially by randomly going, because the planner is uninformed, as it goes closer to these baskets, it will detect some levels of radiation, and as it detects these levels of radiation, so this will happen now in a kind of 2 or 3 seconds. Let me just accelerate it because this robot is kind of going slow. Here we detect above background. So now it propagates all the intensity, believes that all the environment is radioactive, which is not the case actually. So it goes to collect more data to reduce the uncertainty of mean intensity and also of gradients. And therefore it detects that no, actually it was a cluster that led to this, a cluster of sources that led to these intensity values. It keeps exploring the remaining of the environment to reduce the uncertainty for the radiation field, finds the second set of buckets, and therefore also maps the radiation in these conditions, in this environment, again on its own. This distributed radiation mapping, we had some early work that was about point sources, and we have extension of this work now, more for large scale estimation. So this is a flying robot. We are using a new technique about how to represent the environment and also how to factorize the uncertainty, both for the mean value and for the gradient, so both for the intensity and for the gradient, how to propagate these intensities. And the whole idea is that if you know about radiation measurements, the noise of the Poisson process is the same value as the mean, which means that the higher the intensity, the more the noise. And typically the solution is that the robots or the people that use scintillators have to wait and take a measurement over a long amount of time. And we call this dwelling. But actually this is very inefficient, especially for flying robots. So we are doing therefore better integration of the moving values, and we aggregate and organize values all together in cells, and we know how well they are associated, what's the motion between this type of measurements. And this allows us, bottom line, to have a flying robot that is small and can enter an unknown environment again. And here it will use some sort of curiosity planner to go and detect the sources, again, the distributed radiation field from the source, not the sources themselves as units, and map this radiation field on its own. And this robot is using one scintillator only, not 3, purely out of properties of weight. This is the same collision tolerant robot that you saw in the environment that went through the manhole, and therefore it's kind of small, so we do not have the ability to put many scintillators on board. And even the size of the robot does not allow to get a gradient because the 3 scintillators will be very close to each other. All right, I want to close the presentation with a few comments. So this is, we are very happy with the support we have received. Of course, my path as a professor and the results from the group also relate to previous experience I was able to have from a PhD and from ASL at ETH. So, we are all very happy for all the collaboration that also persists between groups. And I want to give credit to the people that actually sat down and did all the work. And that's obviously not only me, and it's mostly the PhD students that work in this research stuff. So here are some of them, and postdocs and PhDs that deployed robots in underground mines. We went in competitions. We had a lot of fun. There's also a lot of stress in competitions, I have to say. So let's give credits to these people. And we have open sourced a lot of the code that relates to what I presented before, our planners. There's also other packages that I don't mention here that relate to how we can improve images in underground environments or generally dark environments and so on and so forth. All those are open source online and one can have a look. And with that, let me thank you and ask you if you have any question. Thanks a lot.
Thanks a lot, Costa. I mean, I don't know, like there is one, here it is, clapping from my side. It's unfortunate that we cannot clap virtually. Thanks a lot for your talk. There are a few questions in the chat, but before going to those, I don't know if anyone that needs to leave urgently has any question, please unmute and ask it before I go to the chat questions. If anyone is really needs to leave and you have any question, go ahead, please. All right, I don't see anybody. So I'm going to start. Basically, there are some questions about the last part and about the first part. So let's go a little bit to the first part. I don't know if you can hear me good because you had some issues. Is it okay? Yeah. All right. So this is before the path planning. So one question is about the localization method. So by Francisco. So he's asking if the standard sparse point detection, matching, tracking from the RGB or grayscale computer vision works well for thermal vision, or do they need some adaptation?
Right. So this is an excellent question, and I can relate it also to the other question I see about loop closure.
Right.
So no, our experience has been that this is not the case. So classical 8-bit descriptors are not working well in thermal in this type of subterranean environments, or generally when you don't have strong thermal gradient. I had a case, we used thermal inertial odometry in the context of autonomous driving. We had a small project, and it works more there because outdoors, because there is direct sunshine, you have actually strong gradients. So it works a little bit better. But truly what we identified is that there is need to utilize the full radiometric information. Now, this does not mean that the principles of traditional computer vision do not work. So we have extended fast to use 16-bit for detection purposes. And we have now a project that relates to extending some of traditional descriptors into the full radiometric information data. And this also relates partially to the question for loop closure. So we're not doing loop closure at the moment, but I think there are two limitations for loop closure. One relates to what I mentioned before. The other aspect is that objects, especially as it relates to different viewpoints, objects may look the same in thermal, although you look at them from different viewpoints, purely out of the properties of the sensing, essentially.
I see. All right. So maybe this answers my question. I had the question about why you don't use only thermal data for doing your localization. I guess this answers this question.
And also because LiDAR is so good when it works.
All right. Okay. So the second question is basically, and I had this question myself, what kind of mapping are you using? So you talk mainly about localization in the first part, but I've seen different type of mapping. So one is octomap based, the other is really the graph that you create. So what kind of mapping and how do you deal with the size of the mapping?
So beyond the SLAM component, which is all the way to reaching to the register cloud, for example, in terms of the volumetric representation, we are using voxblocks instead of octomap. And the basic reason is computational efficiency from our side, and also better handling of a variety of other aspects with respect to query about free volume and so on and so forth. And then for planning purposes, we are utilizing graphs, as you see. So this is for the decision-making of the robot. This is not really the geometric representation. This is where all the decision-making of the robot takes place.
All right, very good. All right, so another question from Ahmad is, I guess this is the picture you had a couple of times with 4 sensors. So it was thermal, LiDAR, etc. And the question is if the fusion happens before the map estimation, or you have a map estimation from each sensor and then you fuse maps, basically?
No. The fusion, at the moment, the fusion is loosely coupled. So essentially, this means that every component operates on its own, arrives with odometry in its map, and one gives cascade priors to the other. Now, we do have work that we try to get the landmarks from every frontend and co-optimize them at the same backend through factor graphs. But this is new work that's taking place now.
All right. Is this the Kalman filtering fusion? What? Or
No. So the fusion that takes place now, every method might be different. So for example, our visual inertia might be Kalman filter based, our thermal inertia might not be, and LiDAR odometry is not, and mapping.
All right. Oh, you are muted.
Sorry. Yeah. Each of them becomes, so we get, for example, let's say we have visual inertia odometry only and LiDAR odometry mapping. Then we will get the transformation estimate from the previous LiDAR odometry to the next LiDAR odometry from VIO, from visual inertia. We will take this, we will pre-align the point clouds, and then we will start from this point now and do the remaining LiDAR optimization and registration, as long as the covariance of the VIO is sufficiently small.
All right. Okay, cool. Next question from Giuseppe is, I guess this is related to the work that you were doing with a mapping of radiation, right? And the question is if this generalizes to other type of environments, so lunar, Mars, lava tubes, etc. So basically not radiation as far as I understand, but with similar characteristics.
Is the question for the radiation part, or is the question for the mapping part? For the 3D mapping or for the radiation part?
Giuseppe, I mean, I don't know, it doesn't say. For the mapping in underground environments.
Yes. So Giuseppe, I can tell you, I think this is a very interesting direction. I do not have the answer to tell you. Actually, I can say some things. So you say lava tubes, but you probably consider lava tubes that are not on Earth. So there are two things. Lava tubes on Earth is something we have been through, and we even have a small unlisted video if you go to our channel, and it has been unlisted for whatever reasons. And lava tubes on Earth, actually, they are visually very interesting. And also LiDAR is reasonably performing well in these conditions. So the multimodal fusion approach works very well on Earth lava tubes. However, off-world lava tubes have two problems that I want to discuss, because I'm actually currently preparing a proposal for this. Due to the smaller gravity, the lava tube there becomes way larger than what we have on Earth. So for example, on Mars, gravity is 38% that of Earth. The anticipation and surface imaging has shown that the lava tubes there can be way wider than Earth lava tubes, which means that some of the sensors will be out of range in these conditions. So there are some fundamental limitations there, kind of more low-level limitations, but I think there is some very nice research that one can consider in this type of lava tubes, not Earth lava tubes. Of course, I have to say also on Earth, you can have the analogs for some of these problems. There exist caves, the Mammoth Cave, for example, in the US, in Kentucky, that are extremely wide. And you can even test some of these challenges here.
All right, okay. I guess this answers all the questions that there are in the chat. I don't know if anybody has any question. I mean, we're a little bit over time. So last chance to unmute and ask question or type it.
Yeah, hi, sorry, can I have a follow-up question, please?
Sure, go ahead.
Thank you very much, Professor Alexis. This was highly informative, really. I'm doing work somehow related to what you presented, and it was highly informative. I had a question regarding the information gain equations that you showed us. One was volumetric gain and the other was exploration gain. And as far as I can see, you kind of merged them into one gain, so they're both kind of codependent in a way. The question is, what if you have information gains which are based on the different subsystems of your robot? How would you be able then to kind of combine them into one information metric in a way? Would the factor graphs you mentioned work in this case, or would it be better to be some sort of Kalman fusion? Yeah. And thank you again.
Yeah, we have two approaches for that. This is a very good question. So we have two approaches for that. We do not add them together. Let me say from the beginning. I have had rounds of discussion about my personal take that let's not add them, because if you add them, I need to come up with some weights that work in all conditions. And I do not want to come with values that should work in all conditions, and then I end up having a wrong tuning. So we have two ways. An old way that we used 2 or 3 years ago, which was that we are going to first prioritize one of the gains, let's say, for example, information gain in relation to volume. We're going to find the best path based on that. We're going to find endpoints on this path. And the way to go to the first point will also change a little bit the motion so as to co-optimize a secondary objective, for example, based on another sensor, for example, based on vision, or for example, based on gas detection or anything. And we have a now newer way, which is a bit more principled, because the one I mentioned before, essentially, we always come and say that one objective is more important than the other. Now we have a new way for which we say the following. The robot, if you, for example, try to explore with a LiDAR, a long-range depth sensor, and also cover everything with your camera, which might be positioned in a very different way, or it might not have the same frustum, and typically doesn't have the same frustum. We can do two things. We can represent the environment topological graph as different distinct type of geometries. Is it a corridor? Is it a big room? And so on and so forth. As you understand, if you're in a corridor, you probably can position the robot and do simultaneously exploration volumetrically and see everything with your camera, whereas in a big room, that's almost impossible. Second, we score the robot. The robot keeps a scoring metric of its performance and questions. Am I doing more exploration and I completely forget visual coverage? Or, for example, am I doing completely the opposite, which is typically not happening in the case? Whenever it detects that it's failing to satisfy both objectives, it allocates an amount of time to optimize for the second objective, for example, visual coverage. It allocates this time, this allotment is triggered, the robot improves its performance with respect to another objective. It reaches again a threshold that says that, oh, this objective is also sufficiently satisfied, changes the game, and goes back to volumetric exploration. And so for that, we are using essentially a game representation with respect to how the robot should interact with the environment.
All right, I guess, Costa, with this question, we're going to finish the seminar. I'm going to stop recording. And I would like to thank everybody for joining today. And we look forward to seeing you in the future seminars of autonomous system. I don't know, Licia, if you want to add.
No, I mean, I just wanted to, I just said very many thanks to Kostas for a great first talk in our seminar series, and many thanks to you, Dimitris, for pushing us to get this off the ground. Our next talk is in about a month's time, 22nd of February. Same Zoom link as this one. Details will be sent a bit later on. So thanks everyone for joining, and have a good rest of the week.
Thank you, Costa.
Thank you. Thank you all.